We're going to continue with properties of limits. And the next property is going to be limit of the ratio of two sequences. But before we formulate the appropriate theorem, let me remind you of the result that we already proved. So let's recall that if I have a sequence Sn, which is going to consist of elements that are not equal to 0, for all n, and this sequence converges, limit as n goes to infinity of Sn is equal to S, which is also not equal to 0. Then we discovered that the infimum for all n of absolute value of Sn is going to be a number which is strictly greater than 0. Okay, so with this in hand, let's prove the following theorem. Suppose that Sn satisfies the same conditions that I have just listed. Now, remember that this theorem that I just mentioned, we proved, I think, 2 lectures ago. So if Sn satisfies exactly the same conditions, okay, suppose that this is true, then the limit as n goes to infinity of 1 over Sn is going to be equal to 1 over S. Okay, so which seems to make sense, right? Because if Sn is not equal to 0, then 1 over Sn is going to be defined for all n. And if S is not equal to 0, I would expect that the limit is equal to 1 over S. So let's first outline the idea of the proof again. So what do we want? We want for n epsilon greater than 0, we want 1 over Sn minus 1 over S to be less than epsilon. Okay, so let's analyze this 1 over Sn minus S. What do I know? I know that Sn converges to S, so I can make absolute value of Sn minus S small. And in this case, I have to make 1 over Sn minus 1 over S small. So that means that I have to algebraically change 1 over Sn to minus 1 over S. I want to change it to an expression which will contain Sn minus S. And the way to do it is to put this difference under common denominator. So 1 over Sn minus 1 over S is going to be an absolute value, the absolute value of S minus Sn divided by Sn times S, absolute value. And of course, I can then distribute absolute value between different terms in the product and in a ratio. And I can also interchange Sn and S because absolute value of Sn minus S is the same as absolute value of S minus Sn. So this is the same thing as absolute value of Sn minus S divided by absolute value of Sn divided by absolute value of S. All right, and so then what do I know about this? So from what we just proved, we know that the infimum of Sn is a number which is strictly greater than zero, right? So infimum of absolute value of Sn, so by the result above, this infimum is strictly greater than zero. I can write it as that this is equal to some little m, which is strictly greater than zero, right? And if infimum is strictly greater than zero, then actually one more thing that I can say here. How is infimum of Sn related to absolute value of Sn? Of course, absolute value of Sn is greater or equal than the infimum. And this should be true for all n, which is a natural number, right? So for all n greater or equal than 1, Sn, magnitude of Sn must be bigger than m, which is bigger than 0. But if absolute value of Sn is greater or equal than m, then 1 over absolute value of Sn must be less or equal than 1 over m, right? So if Sn, absolute value of Sn is greater or equal than little m, a positive number, then 1 over absolute value of Sn is less or equal than 1 over m by properties of ordered fields again. And so then I can utilize this expression above. So then this is less or equal than Sn minus S divided by little m times absolute value of S. All right. And so this is true because by the result above, etc. Okay, so then I'm going to require that 1 over Sn minus 1 over S, that this, which is already less or equal than Sn minus S m absolute value of S, I'm going to require that this larger number is less than epsilon, which is the same thing as requiring that Sn minus S is less than m absolute value of S times epsilon. Now, m times absolute value of S is a known constant, and Sn minus S I can make as small as I wish. So then this fact should allow me to make 1 over Sn minus 1 over S to be as small as I wish. And so now let's convert this to a proof. So choose any epsilon greater than 0, since the limit n goes to infinity of Sn is equal S, then by definition of the limit, there exists a capital N such that Sn minus S is less than M absolute value of S epsilon if N is bigger than capital N. Again, there exists a capital N such that Sn minus S is less than whatever number I chose in the beginning. So in particular, I can make this number M absolute value of S epsilon. Okay, so then if that is the case, so then if N is greater than capital N, we just have exactly this chain of inequalities. So copy. And this is less than what Sn minus S is less than M absolute value of S times epsilon. We divide this by M times absolute value of S. Those two cancel out. And this is equal to epsilon. And that means that we're done because for every epsilon greater than 0, there exists a capital N in R such that 1 over Sn minus 1 over S is less than epsilon. And so that's it. That means that we satisfy the definition of a limit for 1 over Sn, and the proof is complete. Okay, so now let's prove the next theorem. I'm going to utilize exactly the same conditions as here. So if I know that a limit of 1 over Sn is equal to 1 over S, and if I know that the limit of the product is equal to product of limits, then I can conclude something about the limit of the ratio of two sequences. So I'm going to suppose the same conditions for Sn and assume also, that the limit of Tn is equal to T. So then we should expect that the limit as n goes to infinity of Tn over Sn must be the same thing as T over S, or the limit n goes to infinity of Tn divided by the limit n goes to infinity of Sn. How would we prove this? We're just going to appeal to the two previous theorems. So, first of all, by the previous theorem, we have that the limit n goes to infinity of 1 over Sn is equal to 1 over S. And so then the limit as n goes to infinity of Tn over Sn, I can represent as a limit n goes to infinity of Tn times 1 over Sn. And then the limit of the product is a product of limits. This is the same thing as a limit n goes to infinity of Tn times the limit n goes to infinity of 1 over Sn, because both of these sequences converge. And then this must be equal to t times 1 over s, which is which I can write also as t is a limit n goes to infinity of tn, and 1 over s is 1 over the limit n goes to infinity of Sn, right? So the limit of the ratio of two sequences is going to be ratio of two limits as long as Sn is never equal to 0 and its limit also is not equal to 0. So we're done. So in this case, we already don't need to use properties or definition of a limit. We can just use the properties that we have already proved. So we use two theorems. One is that the limit of the product is a product of limits, and another one is the product of a reciprocal is the limit of a reciprocal is reciprocal of a limit. All right. So this establishes a basic algebra of things that you can do with limits. And now let's look at the limits of some elementary functions, because if we have those, then we can combine limits of those elementary functions with uh, properties that we've proved already to combine the elementary functions to functions that are more complex. So, next theorem. We're going to talk about some basic limits. Number one, limit as n goes to infinity of 1 over n to the power p is equal to 0 if p is greater than 0. Let's prove this assertion. So proof. So here you would have to use a definition of a limit. Let's choose any epsilon greater than 0. Now what do I want? I want 1 over n to the p to be less than epsilon. And I can achieve that by solving an equation 1 over n to the p less than epsilon, and that would require me to make n larger than little n larger than 1 over epsilon to the 1 over p. So make n 1 over epsilon to 1 over p. Again, basically I'm just solving an equation 1 over n to the p less than epsilon. So then, if n is bigger than capital N, what do we have? We have that 1, so we have 1 over n to the p minus 0 absolute value, which is, of course, just 1 over n to the p because everything is positive and 0 does not affect anything. Well, so if n is bigger than capital N, so n bigger than capital N, that means that if I raise both of these guys to a positive power, then n to the p is going to be greater than big N to the p, right? Because power of any positive power of x or n is going to be an increasing function. So the inequality is going to be preserved. And then if I take 1 over n to the p and 1 over big n to the p, then the sign of inequality should reverse. So 1 over little n to the p is going to be less than 1 over big N to the p. Okay, so then this guy up here is less than 1 over big N to the p. But who is big N to the p? It's 1 over epsilon to 1 over p. So we have 1 over epsilon to 1 over p, all of that raised to the power p. And if you then follow this, this would be 1 over 1 over epsilon, right? Because powers p and 1 over p will cancel out, which is equal to epsilon. And then I'm done because I was able to select capital N for a given epsilon, which guarantees that 1 over n to the p minus 0 is less than epsilon. So the proof is complete. Okay, number 2. Limit as n goes to infinity of a to the power n is equal to 0 if absolute value of a is going to be less than 1. Okay, let's see. So we have a couple of choices here. Let's do the proof. Choice number 1, a is equal to 0. And then the proof is trivial because a itself, or absolute value of a to the n, this is equal to 0 for all n, and the limit of a constant sequence is that constant. Right, so if I have a sequence that consists of all zeros, then the limit must be 0. All right, part B. I'm going to suppose that absolute value of a is greater than 0, but less than 1. And then in that case, I should be able to write absolute value of a as 1 over 1 plus b for some b that is positive. The way to show it basically is to solve an expression b equal to 1 minus absolute value of a. Minus 1 over absolute value of a minus 1 be equal to that. And this should be positive. So we have that. And then what we have is that absolute value of a to the power n must be equal to 1 over 1 plus b to the power n. And in that case, this can be, of course, simplified to 1 over 1 plus b to the power n. And let's say that now I want to show the following inequality. And I'm going to do it separately from this proof. Let's try to show the following. So if I have 1 plus b squared, this is 1 plus 2b plus b squared. If I have 1 plus b cubed, you might remember this is 1 plus 3b plus 3b squared plus b cubed, etc. So if I remove b squared from here, then 1 plus b squared is greater than 1 plus 2b because I removed something positive. If b is a positive number, right, like it is in this case, then also 3b squared plus b cubed is a positive number. So if I drop it, I'm going to make the right-hand side smaller. So same thing here. This is gone. And I can put a greater sign. Right, so this is for b greater than 0. And then I would expect that it should be true that 1 plus b to the power n, that this must be bigger than 1 plus nb. Well, so how do we prove something like this? We prove this by using induction, right? So let's try to do that. So the base step we already showed. In fact, let me just rewrite this. So I'm going to get rid of these things that allowed us to make a conjecture. And I want to prove that if b is greater than 0, then this inequality will hold. Use induction. So first, base step, 1 plus b to the first is actually, this should be greater or equal. 1 plus b to the first is equal to 1 plus 1 times b. So this is true. Induction step, we're going to assume that 1 plus b to the n is bigger than 1 plus nb. And I need to show the same thing for 1 plus b to the n plus 1. So now what is 1 plus b to the n plus 1, right? That's 1 plus b to the n times 1 plus b. According to the m step, this is bigger than 1 plus nb times 1 plus b, right? Because I'm multiplying 1 plus b to the n and 1 plus nb by 1 plus b. So basically what I did, I just took this inequality and multiplied by 1 plus b. All right, and then if I distribute, this is 1 plus nb plus b plus nb squared. Well, but this is positive. The nb squared is positive. So if I drop it, I can only decrease the expression. And how much is left? It's 1 plus n plus 1b. And so we're done. Right? So by induction, 1 plus b to the n is greater or equal than 1 plus nb. All right. So then if that is the case, then 1 plus b to 1 over 1 plus b to the n should be not greater, but less or equal, right? Because again, I'm taking inverse of two positive numbers. And if the inequality holds for the numbers, then their inverses will satisfy the opposite inequality. So this is less or equal than 1 over 1 plus nb. And if it is less or equal than 1 over 1 plus nb, then if I drop 1 from the denominator, I'm only going to make, because 1 is positive, I'm only going to make this expression larger. So this is less than 1 over nb. All right. So now, given an epsilon greater than 0, I'm going to set capital N equal to capital N equal to 1 over epsilon b. Then, what can I say about absolute value of a to the n minus 0? This is the same thing as absolute value of a to the n, which according to my computations that I just did, this is less than 1 over nb. But if n is bigger than capital N, then this is less than 1 over 1 over epsilon b times b if n is bigger than capital N. But then what is this, right? B is going to cancel out, and 1 over 1 over epsilon is equal to epsilon. So in fact, I can just move if down here and say that this is equal to epsilon. So if epsilon greater than 0, I was able to select capital N to be this number. If n is bigger than capital N, then the difference between a to the power n, magnitude of a to the power n, and 0 is less than epsilon. And so we demonstrated the definition of a limit for the function absolute value of a to the power n. All right, so and then in the next lecture, I'm going to consider more of these basic limits, and then we will talk a little bit about computing limits using properties, just like you did in regular calculus.